check first thing in tomorrow, and if you have not received it by then, let me know or let Miss McKinney know, and we can try to help you out. But the bottom line is, you can still go to your AP classroom login, and that ticket should be there, and you can just click the link and go from there. Also, I sent yesterday some guidance about using your phone. Make sure you have it set to save your pictures as JPEG, I think. And honestly, I wish I had known this about, I don't know if it's just iPhones or if it's all phones, but this HEIC format. I found when I was grading work in classroom that some students, not just stat students, but all my students who would send me pictures, some of them I could browse through and expand and contract and move up and down with no problem. Others of them, it was like the image was frozen on the screen. I could do nothing with it. And I found out later that it's this HEIC format that phones are somehow able to store. I don't know anything about that format, and so I don't know what's going on. But anyway, make sure if you're going to take a picture that you have your phone set to the right format. And Briley, I don't know if you can hear me or not, but the image I see of you is absolutely frozen. So you might want to click out and click back in if you want to. There we go. Okay, so let's get started. A couple of questions that I picked out. One I sent you yesterday about Einstein's theory of space-time curvature. And the one we'll go over today in class. Both of them are really good examples of what I think you might see in terms of confidence interval question. This question today on Einstein is a confidence interval question. The next one I'll show you is a significance test of the difference of two proportions. And you remember, we've talked about this a little bit. The formula sheet you have gives you this long, complicated formula, but you can't go through that formula. So I found a question from 2013, I think. Yeah, 2013. That is a difference of two proportions question, but it doesn't require any calculations. So I think this may be the nature of something you see. And quite honestly, when I put it on the screen, you look at it and it's a pretty overwhelming looking question. But if you read through and you focus on what are they asking, it's not that difficult. Welcome back.
My phone spazzed out.
Yeah, I hope you're not planning to use that for your test.
Well, I am, but
you are. Okay. Well, keep our fingers crossed. By the way, I did send you a link to give you instructions on how to submit your answers if your phone spazzes out during the test. There is a way to do that this week. So make sure you look through that as well. Okay, so let's take a look at yesterday's question, I will send you solutions. Although the answers are really, really short, so I would not expect you to really need a whole lot. 2002. Okay. So this is yesterday's question, and again, it looks pretty daunting. I mean, anytime you see a question that begins, in 1915, Einstein's theory predicted the curvature of space. Anytime you see that question, you're thinking, oh my gosh, I don't know anything about this. But if you read through it, it's pretty straightforward. The graph is certainly worth more than 1,000 words here. So it is certainly something that is within our capability to answer and expect to get full credit. And so it reminds you that these intervals, these confidence intervals, are calculated with a point estimate plus or minus margin of error. And so that's what you see here. The dot represents the point estimator, and then the brackets at top and bottom represent the range of the margin of error, or the range of the confidence interval. So then you definitely have to look at the scale here. The y-axis is value of gamma. The x-axis is really a kind of a timeline, order of experiment from earliest to most recent. In other words, these are the experiments that were conducted closest to 1915. These are the ones closest to current time. And so the question here is, based on the display, describe how the precision of the estimates of gamma has changed over time. Okay, you can know nothing about confidence intervals, and I think just from the graph here, we ought to be able to get that. What would you say about these estimates? How have they changed over time? Briley, you might be on mute.
Oh, I was muted.
Yeah.
What was I saying? They're more confident about their estimate, like as they go on.
Okay, as time goes on, the range of the interval gets smaller and smaller. So the statistics terminology you would use is the estimates become less variable over time, or there's less variation in the estimates over time. Or the positive way to say that, it would be they become more precise over time. In other words, the earlier estimates, there's a great deal of uncertainty. The most recent ones have almost no uncertainty. The confidence interval is very small. So any of those kind of flavors of answer get you full credit. So, I mean, this answer, part A, is one really well-crafted sentence or two sentences will be more than sufficient. Okay. So, but again, it's pretty obvious that the estimates get more and more precise over time. When I look at this graph, the first thing I think of is Star Wars. These look like the Darth Vader ships. I forget what they're called, but I see that and I just want to go pew pew pew. But anyway, let's go on. Part B, write a few sentences describing the strength of the evidence the experiments provide for the claim from Newtonian theory that gamma equals 0. Your response must include justification based on the display. Now, here again, anytime it asks for justification, that does not mean you have to calculate a value or use a formula. Notice it says write a few sentences. Okay, so they're leading you to give a written explanation. There's no way you can do any calculations here. You just don't have enough data. But what would you say about Newton's theory that gamma equals 0? What does this graph tell you?
Like it's very unlikely that it equals 0.
It is very, very unlikely. In fact, the graph provides 0 evidence that gamma equals 0. There is no evidence. None of the confidence intervals contain 0 in their range. So Briley's first sentence is a great lead-in question. It's very unlikely. But in order to get a full score for that, you need to describe that none of the confidence intervals contain 0. And so your justification there is there are 21 experiments. None of the confidence intervals contain 0 in their range, and therefore Newton's theory or expectation that gamma equals 0 has no evidence or no support or no strength, is very weak. Any of those kind of terms would be fine. And so now we look at part C, write a few arguments describing the strength of the evidence for Einstein's claim that gamma equals 1. What will we say there?
It's very likely almost all of the intervals would show 1.
Contain the value 1 is how you want to describe that. But Briley's answer is right on here, I think. Almost all of the intervals contain the value 1. If you want to be really precise and you want to make sure you get all the frosting on the cake, you would say only 1, 2, 3, 4 of the 21 experiments do not contain the value 1 in the confidence interval. Or to put a positive spin on that, you would say the strength of the evidence is very strong because 17 of the 21 experiments contain 1 in the confidence interval. And then you could also go on to say the more recent experiments have a high degree of precision. Almost all of them, with the exception of 1, contain gamma equals 1 in the confidence interval. So you can almost just answer that by looking at the right-hand side of this graph and just say 1, 2, 3. You could say 9 of the last 10 experiments all that have higher precision all contain, or 9 of the 10 more recent high precision experiments contain 1 in their confidence interval. But either one of those, you could focus on the entire picture and say that 17 out of 21 contain 1 in the interval, or 9 of the last 10 focus on the more precise. Either one of those would be more than adequate justification based on the graph. Which pretty straightforward. But what I think a lot of times what they want to do is they want to make the question look daunting, look like it's something very, very hard. But when you get down and you read the question carefully based on the knowledge that we have about what a confidence interval is and the importance that the confidence interval contains a particular value, then I really think that we should get full credit on this question. This one is one that I think you guys will do well on. And again, it's what I would expect to see on the test, where calculations are going to be kind of in the back seat, really. It's more about your understanding of the statistics here. Okay. Any questions? Any questions about that? By the way, if you're a science fan, reading Einstein's initial books on his theories of relativity, they're just incredible. Something made Siri come to life here. Go away, Siri. Okay. So anyway, that's enough of that one. Now let's take a look at today's question. And I apologize I didn't send this to you in advance. I got kind of carried away with something else going on at home, and I didn't get a chance to, but I will send this to you later. You've seen the question. And so honestly, if I were you, I would just kind of sit back and relax and just listen through, ask questions. I will send this to you, and then you can go back, jot notes. You can review the video and jot down notes. I'll also send you a solution to this one as well. But again, you look at this question, you look at the question, and the question itself takes up a whole page. And I know even now, as a a stats teacher for several years, when I look at these questions, I kind of think, oh my gosh. And then I see a hypothesis test that involves the difference of two proportions. Again, I get really, really nervous because I realize, or I remember, when I look at my formula sheet, I remember these formulas here and I think, oh my gosh, look how hard that really looks. Well, it's really not that hard. The concept is pretty straightforward. Again, there's no way they're going to ask you to calculate this on a 4-function calculator. But I really do think a question like this, where they give you the null and alternate hypothesis, I think this is absolutely in bounds. And it may be that they even ask you to come up with, to write the null and alternate hypothesis. And so that's why I want to go ahead and go through this question. So let's just walk through it. Psychologists are interested in the relationship between meditation and health. Conducted a study with a random sample of 28 men who live in a large retirement community. Okay, so the population would be men in this particular large retirement community. That's as far as this goes, because the sample is 28 men, so we cannot make any inference with regard to women. We can't make any inference with regard to anybody outside this community. Okay, so when you read through this, you just need to make sure you understand what the population is. Of the 11 men in the sample, okay, highlight words like sample, because it gives you clues to how you're going to answer. 11 reported they participate in daily meditation. 17 reported they do not participate in daily meditation. So they want to do a hypothesis test where the null hypothesis is PM minus PC. PM is the proportion of men with high blood pressure who participate in meditation. PC is the proportion of men with high blood pressure who do not participate in daily meditation. Okay. So PM is the proportion who meditate, PC is the proportion who do not. And so if there's no difference, if meditation doesn't help, we would expect then this difference to be zero. Their blood pressure should be the same, so we would expect that difference to be zero. If, however, meditation does seem to help, then there should be a non-zero difference. And here they've tested whether the blood pressure of those who meditate, the difference is less than zero. And that's what you would expect. If the men whose blood pressure who meditate is lower, then this difference will be a negative value. Okay. And so again, you have to kind of noodle through and make sure you understand what PM and PC mean. It's really the proportion of men with high blood pressure. So that proportion should be negative if meditation helps. I guess that's the way to look at it. Okay, so read the question carefully. If the study were to provide significant evidence against the null hypothesis in favor of the alternate, would it be reasonable for psychologists to conclude that daily meditation causes a reduction of blood pressure for men in the retirement community? Why or why not? Okay, so what's your initial thought here? What jumps out at you at this point so far in the question? Well, what should jump out at you is the chart from, I believe it was chapter 4, the very end of chapter 4, that we discussed what allows us to draw an inference about a population. And the very first thing we talked about is the only way to draw an inference about a population is to conduct an experiment where you randomly select from the population and you purposefully impose a treatment. Okay, and in this study, did the researchers or did the psychologists impose any sort of treatment? Let me just stay with that. Did they impose a treatment? And remember, a treatment would be something like where one group took a pill, or in this case, one group did meditation and one group didn't, but you randomly selected from the group and said, okay, you guys are going to meditate and you guys aren't. That's not what they did. They just asked them, do you meditate or not? And so this is an observational study. They collected data, and the data is valid. They noticed that the blood pressure of those who meditate apparently was lower than the blood pressure of those who don't. They got a numerical value. But this is just an observational study, and so you cannot draw an inference from an observational study. You have to conduct an experiment where you impose a treatment. And so the answer to this is it is not reasonable to conclude that meditation causes, here's another key word, causes a reduction in meditation, because they did not conduct an experiment. This is only an observational study, and therefore you cannot draw a cause and effect relationship. So it looks like, I mean, there's a lot of words here, and it looks like a very technical description, but when you separate the wheat from the chaff, this is basically a survey. You guys could conduct this survey. You could go into, under normal circumstances, you could go into a retirement community and ask the people who are sitting in the dining hall, would you like to participate in a study? And you ask them a few questions. You guys could do that, and you could get valid data, but you can't draw an inference about cause and effect here, because it's just an observational study. So the answer to part A is it is not reasonable to draw a conclusion because it's an observational study and not an experiment. Okay. Again, I'll send you a more formal and complete response when we're done here a little bit later. Okay, so that's part A, no calculations, just recognizing the difference, being able to interpret what this means, and recognizing the difference between an observational study and an experiment. Okay, so let's scroll down to part B. The psychologists found that of the 11 men in the study who participate in daily meditation, 0 had high blood pressure. Of the 17 who do not, 8 of them did have high blood pressure. So let P hat of M represent the proportion of men with high blood pressure among those in a random sample of 11 who meditate daily, and P hat of C represent a proportion of men with high blood pressure among those who do not meditate daily. Why is it not reasonable to use a normal approximation for the sampling distribution of P hat M minus P hat C? Again, a lot of words here, but the key thing is why is it not reasonable to use a normal approximation? Okay, and so in your mind, what I want you to be thinking about is what are the criteria that we have to satisfy in order to use a normal approximation? What do we have to know that about a population or about a sample before we can say the sampling distribution is normally shaped? Well, for a population proportion, there's one criteria that we have to meet for that shape to be normal. Anybody remember what it is?
Is it the central limit theorem?
Central limit theorem only applies to a population of sample means. So if we had X bar here, we could talk about the central limit theorem. But for a population proportion, there's something else we need to know before we conclude that the sampling distribution is normally shaped.
Is it the 10% rule thing?
The 10% rule only tells us that the data is independent. In other words, there's no dependence from one person to the next. The sample is small compared to the population. And in this case, that certainly doesn't apply. Well, we don't know. We don't know how big the community is. It says it's a large retirement community. And so our sample of 28 men, we could say it's reasonable to assume the 10% condition is met here because the population is large and the sample is small. But that's one of the three conditions for inference. What was the first one? The very first one that allows us to understand the shape is that n times p and n times 1 minus p are both greater than or equal to 10. Okay, so the number of successes and the number of failures are both greater than 10. If those two things are met, then we can say that the sampling distribution of sample proportions is normally shaped. Okay, so here we have to do that n times p hat and n times 1 minus p hat to do our calculation. So the number of people in the sample is 28, 11 and 17. And the number of people who said or who had low blood pressure or who did not have high blood pressure is 8 out of 28. Okay, so that p hat value, if you do the calculation, 8 divided by 28 is 0.286. And n times p hat. So let me just bring up the calculator here and we'll do a quick calculation just to see. So eight men did not have high blood pressure out of the sample, divided by 28 men. So our p hat is 0.286. So n times p hat would be 11 for the group and that did have high blood pressure. So 11 times value That's 3.14. And if I look at the number of failures, if I look at the group of men who didn't have high blood pressure, that's 17 out of that group. So 17 times number 4.85. Neither of those values is greater than 10. And so because of that, we cannot make the assumption that the sampling distribution is normally distributed. So we can't use a normal approximation for this difference. Okay. So one good thing to review before Friday is those three conditions for inference. The first one, is the shape normally distributed for a population proportion? We got to do n times p, or n times p hat, and n times 1 minus p hat. For a sample, a distribution of sample means, that first criteria is if the population is normally distributed, then we can use the normal approximation, or if the central limit theorem applies, like Elijah said. Well, for the central limit theorem to apply, we need a sample size greater than 30. And here we have a sample size of 28. So even if this were a test of the difference between two means, we would be hard pressed to say that the central limit theorem applies, because we need n to be greater than 30. And so that's one of the criteria. The second criteria is that the data needs to come from a random source. And if you go back up here and look at this, we are told that the data is from a random sample. So we do meet that one. And we probably meet the 10% condition, but we do not meet the criteria for the use of the normal approximation here. Okay, so those three criteria we've got to meet. And just make sure you keep in mind, and let me think, does this? No, this doesn't give you any hints. It is completely fair in this year's test, when you print this out, to write down the criteria for sampling distributions for proportions. Okay, the criteria are this: random sample, normal approximation, and 10% condition. Those three criteria are the same for a sample distribution of proportion or a sample distribution for means. The criteria are the same. How you determine them are different between proportions and means in terms of the second one, that you can use the normal approximation. Okay, so just be clear on that. And we've got, I tell you, I'm going to make myself a note here today at the end of class. I'm going to add a couple of note pages for the conditions for inference, just so that you'll have that in front of your nose. But it is perfectly okay for you to write on this formula sheet for this year. Last year or next year, you couldn't have done that. Okay, the formula sheet is part of your test packet and it comes to you ahead of time. But this year, you have that advantage. I would use it. I would jot some notes down here, so that it's clear in your mind what that's all about. Okay, so what are you doing? I don't know why you're doing that. What's happening here? Okay, so let's look at part C now. Okay, so although a normal approximation cannot be used, it's possible to simulate this distribution under the assumption that the null hypothesis is true. The histogram below shows the results of the simulation. Based on the results, what can be concluded about the relationship between blood pressure and meditation among men in the retirement community? Okay, so let's see, the sample statistic the sample statistic p hat over m, and maybe I should flip on the monitor here. Let me do that real quick. You got to plug it in, you doofus. Now we got it. Okay. All right, so let me get you guys back on my screen. Can you see my whiteboard here? Can y'all see that? Can you see the smiley face? Yeah, okay. All right. So what we're testing here is the difference p hat of m minus p hat of c. And we have these values. We can calculate the proportion of men who meditate, who have high blood pressure, and that's 0 out of 11. Okay, and then the proportion of men who do not meditate that have high blood pressure is 8 out of 17. So if we calculate that difference, that's a value of negative 0.47. Okay, so if we calculate that difference, then we get a negative 0.47. Okay, so now we need to go back to the graph now, and let's take a look at the graph. And we see that it is centered at about negative 0.02. It's centered very close to 0. And the value of negative 0.47 only occurs 76 out of 10,000 times. Okay. So what we can say here is that while that observation is very, very, very rare, it's very rare that we get a value this low. If the null hypothesis is true, that Pm minus Pc is equal to 0, then the value that we get, the number of times in our simulation that we got a value as low as negative 0.47 is so small. In fact, if you calculate it, 76 divided by 10,000 is 0.0076. No, I'm sorry, 0.0076. So it's 0.76%. It's less than 1%. Okay, and so that p-value is very small. So there is convincing evidence that because the p-value is so small, there is convincing evidence against the null hypothesis, okay? So although we conclude that it is associated, meditation and low blood pressure are associated, we can't say that there is a cause and effect relationship. And that's the real important part of this question, okay? Is that there may be an association. In fact, there's convincing evidence that there is an association between the two, but we can't say that there is a cause and effect relationship going back to part A. There was no experiment done. So we can't say that there's a cause and effect here, okay? So again, let me write this down so that you can read through it and get in your head what I'm trying to say here clearly. But the point is the p-value is low. So there is evidence against the null hypothesis here in favor of the alternate. But because this was not an experiment, the strongest thing we can say is there's an association between meditation and low cholesterol. I'm sorry, low blood, an association between meditation and an absence of high blood pressure or hypertension. I don't know if any of you are taking the medical terminology, but hypertension. But there's no cause and effect relationship. So the reader is looking for the code word cause and effect or association here as much as your interpretation of the graph, okay? So again, the p-value is low, so there's evidence against the null hypothesis. But we cannot conclude a cause and effect. All we conclude is a positive association, okay? So again, this question demonstrates a solid understanding of significance testing. It also demonstrates an understanding of the difference between an observational study and an experiment. So there are two skills here that are being tested in this question, and the hardest calculation you have to do is 0 over 11 minus 8 over 17. Okay, so this is not a calculation intensive question, but man, does it demand a good understanding of two very important statistics skills. Okay, so I could see a question like this coming to you. So be prepared. All right. I will, like I said, I'll send you written solutions for both of these today so you can have them to go over. My hint for the day, jot down some notes on your formula sheet. There's no prohibition against that. No prohibition against taking these little tab Post-it notes and putting them in your textbook or your notebook binder. I don't know. I have a feeling a couple of you, your notes are pretty organized, but some students may not have kept good notes during the year. But the textbook, man, you can just flip through the textbook and those main dialogue definition boxes, put a sticky note there. And there's no prohibition against doing that this year. Now, the thing is, if you're constantly looking at your textbook, time is going to tick by really, really fast. But again, the emphasis is answering the questions that you know thoroughly. It's not about answering a lot of questions at a low level. It is more about answering a few questions thoroughly. And if you do that, then you can be confident that you'll get a good score. Again, I think this is a really good prep for this year's test. Okay. Any questions from the group here? We all good? All right. Well, tomorrow we'll get back together at 1. I'm really not planning to do a class on Thursday. I really want you just to relax on Thursday. Again, if you want to go through and spend some time organizing your notes or putting sticky note tabs in your textbook, just to on a low level kind of review so that you know where things are if you need to look them up. But don't get in the habit, or don't allow yourself to think, well, every time I come to a part, I can look it up in the textbook, because 25 minutes is not a long time. I mean, we've been online here talking through these questions for 40 minutes already, and we covered, 2 questions. Now, again, I went into more depth than I would have to answer the question, but there's a fair amount of writing for this second question that we did. You'll have to write quickly to get through it. Okay. All right, gang. Well, hang in there. And if you can, go get you some Chick-fil-A chicken nuggets for lunch, because they look really, really good. For those of us who haven't had lunch yet, they do look really good. All right, guys.
They are very.
I'll see y'all tomorrow. Take care.
Bye.